In this lecture, we want to talk about the geometry of linear combinations, and the way to think about this is in terms of directions. So if you've got like a two-dimensional map, like a grid, then you can navigate this map, or in real life, using these four cardinal directions. So north, south, east, and west. And typically, if you go to like MapQuest or something, they give you directions in terms of north, south, east, and west, you know, turn right, turn left, that kind of thing. So let's say we've got a two-dimensional map, and the question is, can I tell you how to get anywhere on the map using these four directions? Can I tell you how to get anywhere on this map using fewer than these four directions? So here's an example. So let's say we're on this map, and we've got Broadway Street, this vertical, and we've got Main Avenue. So at the intersection of Broadway and Main is the origin. And so we'll assume here that streets run north and south, and avenues run east and west. So for example, if I go this way 2 and this way, let's say 3, then the street I am on is 2nd Street, and we'll say 2nd Street East. And then over here would be 2nd Street West, right, like we do here in the hometown of NDSU. So, can I tell you how to get anywhere on the grid using north, south, east, and west? So how do we interpret north, south, east, and west in the context of linear algebra? Well, if you think about what it means to go north 1 block, that's this standard basis unit vector 0, 1, right? So 0, 1, that's 1 block north. And then what should east be? If we want to think of the direction east as a vector, well, that should be 1, 0. So 1 block east is this vector that points in the positive, right, on the positive x-axis. So that's the vector 1, 0. And then south, 0, -1, right? So 1 block south. And then 1 block west is going to be -1, 0. So these are the four vectors. They are basis vectors. Not all 4 of them taken together, but you can take 2 at a time and make a basis. But I can tell you how to get anywhere, get to any intersection on this grid using these 4 directions. So what does a linear combination of these directions look like? So here's a list of instructions. If I say go 5 blocks east, so 1, 2, 3, 4, 5, so 5 blocks east, and then go 5 blocks north, 1, 2, 3, 4, 5. So now we're here. And then go 3 blocks west. So 1, 2, 3. So now we're here. And then say go 3 blocks south. So 1, 2, 3. So now we're here. And then go 1 block east. So now we're here. And then go 3 blocks south. So now we're here, I think, or unless we're over here. But anyway, we'll work this out in a minute. So where should this land us? If I go 5 blocks east, 5 blocks north, 3 blocks west, 3 blocks south, 1 block east, 3 blocks south, how can I write that down as a linear combination of these 4 direction vectors? Well, altogether, I went 5 blocks east, and then I went 1 block east. So now, all day, that means I went 6 blocks to the east. So that's 6 times that vector, that east vector, 1, 0. And then how many blocks north did I travel? Well, here I traveled 5 blocks north, and there's no other north in the list. So I went 5 blocks north. That's 5 times the north vector, 0, 1, right? So 1 block to the north is in 0, 1. And then how about traveling west? So I traveled 3 blocks west here, 3 blocks, well, that was all we did, 3 blocks west. So 3W, 3 times -1, 0, right? West is -1, 0. So 3 times -1, 0. And then how many blocks south did I travel? So 3 and 3, so that's 6 blocks south. So 6 times 0, negative 1. So if I add all this up, right, just using the standard scalar multiplication and vector addition, I wind up with 3, negative 1. So 3, negative 1 puts us right here. And so where are we located? So now we're located 3rd Street East, right, because we're east of the origin, 3rd Street East, and then what's the avenue? So it's the 1st Avenue but south. So 3rd Street East, 1st Avenue south is where we will wind up. So all of these directions, we could have just said, go 3 blocks to the east and then go 1 block south. We could have just said that, right? That's a simplified, right? A simplified linear combination, one that's easier than this, but we got to the same location maybe using a shorter list of directions. So this is the idea behind span. So for example, 3, negative 1 is in the span of these 4 vectors, east, north, west, and south, because I can write 3, negative 1 as a linear combination of these 4 vectors. And the question is, can I get anywhere in this grid just using these 4 vectors? So for example, up here, right, what is that? 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. So up here, 5, 5. How can I describe how to get to this point using just these 4 directions? We'll really only need 2 of them. If I go 5 blocks east and then 5 blocks north, I will get to the location that I'm trying to get to. Pick anywhere, right? Any old A comma B. You go that many units along the x-axis forward or backwards, and then B units along the y-axis to get where you need to go. So the point is that you can get anywhere on this grid using these 4 directions. And in fact, you can get anywhere on this grid just using 2 directions. So for example, we could just use north and east, or we could just use north and west, or we could use south and east, or we could use south and west, right? So we can get anywhere just using 4 directions. So for example, or even the 2 directions, let's say here. How do I get here? Well, I would go, if I just wanted to use the vectors north and east, I would go 1, 2, 3, 4, so negative 4 units using the east vector. Even though I'm traveling west, it's the opposite of east, I would go negative 4 in the east direction, right? So east is this way, negative 4 east is this way. And then I would go 2 times in up here, right? So this is where I would land at negative 4, 2, right? Negative 4 east, and then go 2 in the north direction. So this is the kind of thing that we want to think about in this section. We want to think about, does a set of vectors span a space, 2-dimensional, 3-dimensional, and higher? And what is the set of all reachable points? If I hand you a set of vectors, if I hand you a set of directions, can I use those vectors to reach anywhere in the ambient space? So these are the kind of things that we want to think about for this lecture.